how about the sketch of the curve? Are you able to sketch that curve? Something that's kind of a little bit review what we've done before. So we got this vector function 3t t squared plus 1. Hopefully we can sketch that. So how would we go about sketching that? 3t t squared plus 1. What can you say about that right off the bat?
It's a parabola.
Parabola?
And the x equals 3.
He says, and the plane x equals 3. So compared to the screen here, if this is the screen, here we are on the screen. What is the plane x equals 3? Where's that? 3 forward, right? So like go 1, 2, 3. So we're in this plane, x equals 3. And then what parabola do we have?
The bottom parabola is at z2.
So can we write that without t? Can we write that without t?
Well, the y equals y, z equals y squared plus 1.
So z equals y squared plus 1. So in the plane z equals 3, we are x equals 3, we have the parabola z equals y squared plus 1. What does that look like?
Parabola vertex starting 1 unit up.
So 1 unit up, this,
Yeah.
and then?
On that.
Something like that. And that's in the plane z, x equals 3. Okay, cool. So what I wanted to tell you, so then t at 2, so at t equals 2, what point are we on in the curve at t equals 2? 3, 2, 5. So 3, 2. So it's somewhere on this side. So my proportions aren't great here. I'm just going to throw it here, okay? So this is the point 3, 2, 5, just for the sake of the picture. But my scale isn't great, but it's somewhere on the right side of the parabola, right? Is that fair? Okay. So what will the t vector be like? What will the capital T of 2? So t of 2 will be like what? Yeah, David. Right. So like use a clock to tell me which way should the hand point. Like noon, 3, 6, 9. Yeah, like 1 o'clock, right? Something like that. So that'd be t of 2. How about n of 2? So there's all the formulas for these, right? There's all the formulas for these. You plug in 2 and you get vectors, right? But then there's just looking at the picture and just sketching them. And that's totally separate. And then you could use both to compare with each other, right? So you could understand what t is and n is and b is, and then sketch those from your the concept of them, and then do all the algebra and then compare to make sure that they're right. Does that make sense? Okay, so what about n of 2? Tell me using the hands of a clock. What about n of 2? 3 o'clock, 9 o'clock, noon, 6, 7. 9? 10, right? So it's going to be orthogonal to this, somewhere like 10. Okay, and so then, like I said, when you put in 2 into your formulas for these functions, you should get vectors that are like this. And both those vectors have what? They have a what? X component of what? So they should have an X component of what? No. 0, right? No change in X, right? Components of vectors are like the amount of change, right? So if they're in the plane X equals 3, then all their X components should be 0. Does that make sense?
Yeah.
Okay, so without doing the cross product of t and n, we can just kind of write down what b is, right? If we understand that it's orthogonal to the, did we talk about the osculating plane? Yeah, we did. The osculating plane. That's like the plane that the curve is in. And the B is orthogonal to that. So the unit vector orthogonal to the osculating plane. What's the osculating plane? The osculating plane is the plane that the curve is in. X equals 3 in this case. Always. No matter what point you're at, the curve is always in the plane x equals 3. So the osculating plane is x equals 3. So then what about the B vector? What would it have to be? Pointing which way? What's that? Yeah, it's going to be perpendicular to this. So either at us or into the screen, right? Either at us or into the screen. Which one? So that's right-hand rule, right? T cross n. T cross n. T cross n at you. So Max, is that what you said? Yeah. Right. So T cross n. T cross n at us. So you can just write it down, right? So no calculations. What is the unit vector pointing right at us? What's the unit vector that points right at us? 1, 0, 0. So that's what I meant by this hint here. The fact that osculating plane is the plane of t and n. It's the plane that the curve is in. At that moment, the B vector is orthogonal to that. So the curve is always in the plane x equals 3. And so then the B vector would be orthogonal to that, and as a unit vector, that would just be 1, 0, 0. Now, if you plug in 2 to t, plug in 2 to n, do the cross product, you should get that. If you do the cross product, you should get 1, 0, 0. Algebraically, too. What questions on part 1 of the homework? Questions on part 1? Yeah, David.
This was wrong. What about
What's that? Yeah, no, that's oscillating. That's oscillating. So they're going back and forth, right? So that's different than that. You know what? I really don't know. There's another. So in the osculating plane, there's something called the osculating circle, which we're not going to cover. The osculating circle, it's in the osculating plane, and it has the same. It's the circle with the same curvature as the curve. So you can imagine a circle that has the exact same curvature as the curve at that point. So see if I can draw a good circle. Oh. So that right there would be like the circle that has the same curvature as the black curve, as our vector function curve at that point, and tangent to the curve at that point. So there's the same amount of curvature right there. That's called the osculating circle. But that's another thing that has the word osculating, but I actually don't know exactly what the meaning of osculating is. But I know the osculating plane is the plane that the curve is in, and the osculating circle is the circle that's in that plane that has the same curvature as the curve at that point. So as you move this way, that circle will get smaller and smaller because the curvature is higher at the vertex. So that circle will get smaller and then bigger again over there. But we could just Google it and find out. What's that? All right, other questions about part 1 in the homework? Okay, so part 2, we're just gonna move on from part 2. I think that's just a matter of plugging into the formulas that we gave you last time, the dot product and the cross product formulas. If you need help, please get me out of class. So in terms of getting help on the homework, I'm just coming every day before class at around 12:30. So I won't announce that anymore. I'll just be here. I'll be around. I'll be out in this lobby out here or in this little room next to our classroom. So please take me up on that. And then you can also email me questions if it's not too complicated. All right, you can over the weekend or in between classes. So get the help you need. I want to be, available to support you. So if there's things you don't understand in the homework, which inevitably there will be, find me either by email or before class and get your questions answered, okay? All right. Number 3, I wanted to talk a little bit about number 3. There's a couple things on there. And then we're pushing that to Thursday, okay? That'll be included with Thursdays. So there should be a lot on there that you were able to get, and that's good. I just wanted to show you one thing. So suppose we have this curve in R2. Let's say f of x equals x cubed minus 1, okay? So something like that. One more try. That's better. Okay, something like that. All right. And so let's come out here at 2. So I want to come up with I want to get the t and the n vector at 2, say. Because we know that the t and the n vector, those give us the direction of the 2 components of acceleration, right? The t vector gives us which direction of which component of acceleration? Yeah, and what kind of acceleration is that? Tangential acceleration. What's that about? What's the tangential acceleration? What is it?
Speeding up or slowing down.
Speeding up or slowing down, right? So the t vector is the direction of this part of the acceleration that's strictly due to speeding up or slowing down, like the everyday kind of acceleration that we think of. But then we saw last time that there's more to acceleration, right? What else causes an object to accelerate? Just changing direction is acceleration. And so what's the direction of that acceleration? N, right, good. So we want to come up with the t and the n vector. So t vector, again, using a clock, what would the t vector, which way would it point right now?
1.
Yeah, again, like 1 o'clock, maybe. Like that. So this is t of 2. And then, what about the n vector? If I'm coming this way. He wants 10. Is it 10 or 4? So which way are we turning, left or right? Turning left, correct. Turning left, correct. So it would be 10 again, like this. So how can we get those vectors? How can we get those vectors? We don't have a vector function, right? But we have the actually just a real value function, right, of one variable, like we've been dealing with your whole career. So how can we get t of 2 and n of 2 without a lot of algebraic fuss, right? So any ideas we can do here? Yeah, Kyle.
This is a different question, but is n of 2 the direction the curve's going or direction the tangent's going?
It's
orthogonal.
It's orthogonal to the tangent, and it's how the tangent is changing, right? So it's the direction that the tangent is changing. So if I were to draw the next, so if this is t of 2 like this, then the next one would be a little bit steeper. Do you see that? So say this is t of 2, then like t of maybe like 2.1 would be a little bit steeper. Do you see that?
Oh, because the curve's shifting more and more.
Yeah, the curve is kind of turning to the left. So then n is the direction of the change in those. So n, this direction of n is like the direction of t of 2.1 minus t of 2. And what direction is that? Ooh. I don't know. Wow, sorry. Yeah. Yeah, I meant the button. Oh my gosh, what's going on? Okay, I think oh, maybe it's because I'm over here. No, it's okay. All right, so which way is T of 2.1 minus T of 2? You see it's like there? So it's like the N is representing the change in T. And T is the direction of motion, right? T is the direction of motion, so the change in T, as you go up this curve, T is changing like this. So boom, it's like the direction of turning.
Showing you which way that tangent is sweeping as it goes more and more.
It's through how it's changing, right? So it's the change in direction, which is like the direction of turning. Does that help? Yeah. Okay, so how can we get T of 2? So what is it? It's tangent to the curve, right?
Mhm.
And what about f of x can help us get like something tangent to the curve?
Just find the derivative. And then plug it.
Okay. So the derivative, what is the derivative here?
That's the instantaneous.
Okay. So it's 3x squared, and then at 2. What's at 2? It's what? 12?
So 12.
So if the rate of change is 12, how does that help us find this vector, right? So a vector is made up of components, right?
112.
What's that?
Was the 12 how much it went up for 1 unit of time? So it's
Good.
just 112.
Oh, for 1 unit of what? This is so.
Of x.
Yes.
20 of x.
Good. Right? So how can I kind of label this triangle here?
So the x is 1 and the y cosine is 12.
Right. So this is like the ratio of rise to run, right? The rate of change in the geometry sense is like slope. It's the ratio of rise to run. So if the rate of change is 12, then we can know that this is going up at it's the y change is 12 times as much as the corresponding x change. But is T2 1 comma 12? Well, what kind of vector is T2?
Oh, yeah, you have to find the unit vector. So you have to.
So it's 112 divided by square root.
It's.
Square root of 145. Now so we use the derivative and we got the ratio of y change to x change from the derivative, 12 to 1. We made into a unit vector, so that's T2. For this example, we'll have x cubed minus 1. All right, now what about N2? We definitely don't want to, find the derivative of T and then normalize that like what N is. Rather, we want to use what we know about T to find N. So what can we do? It is. Yes, it is. So if this is a 1 to 12 ratio, then what about the orthogonal vector? He wants negative 12. And what verifies that? Two vectors are orthogonal if? Dot product is 0. Is the dot product 0 now? Negative 12 times 1, positive 12 times 1. So we can write down what N2 is without doing all that awful. What is the N2 vector? No, we need a unit vector again. So what will it be? Negative 12 over 145. Yeah, so that's what I want to show you. So in R2, here's a nice way to find an orthogonal. Given one vector, find a vector orthogonal to it. right? If you know the components of the one, then if they're going to be flipped, and the one will be opposite to get the, and you just follow, negative x, negative directions of positive and negative x and y to determine which one is negative and given your starting vector. So does that?
Only in R2.
This is an R2 technique. Well, or you could do it in R3 if you're like, say in that last example, in the plane x equals 3. Then you basically have an R2 situation, right?
Yeah.
But as soon as the curve is like oblique in space, then it's harder to do this. Yeah, Sebastian?
This wasn't a specific problem, right?
I made this one up to help you with the worksheet. So I made up a new problem with f of x equals x cubed minus 1. So your function is a little different than that. So everyone see how I got t2 from the derivative and then n2 from t2 using this orthogonal R2 vectors technique. Any questions on that? Okay, so then this worksheet is really, really important for putting all this stuff together, putting together the t vector, the n vector, the components of acceleration, and the second derivative. All puts it all together. So rather than just going for the answers, make sure you're thinking about like what is this trying to teach me? What am I supposed to be understanding here about the relationship between all these different functions and acceleration and the path of the object? Okay, there's lots of really good stuff in there that is applying all the stuff we've been learning in class. Okay, any questions on that? Okay, so the only request was for, Sebastian, was it 32 or 36 that you posted? Didn't you post a homework question? 32. Okay, let's look at 32. Okay, so this was the book problems were about these multivariable functions. Here's an example of a multivariable function that the body mass index, BMI, is a function of weight and height. Okay, and that is W divided by h squared. So this is one of these new kind of functions that we started talking about last Thursday, where you have two independent variables. And based on values of those two independent variables, it spits out or gives you a third quantity. In this case, it gives you something called the BMI, body mass index. So what's the BMI if the height is 1.72? What's that? Is this not familiar?
No, because I'm the wrong chapter.
12.1.
12.1?
Yep.
No wonder I was so confused. I was in 12.6.
Yeah, there you go.
And it was like
That would, yeah, I would have questions about that too.
find a function that is continuous in this limit and non-continuous in this limit.
Uh-huh. So how would we, we've already started, let's talk about this one. So how would we plug values in? So we can represent the body mass index without doing anything, but just write B of 72, 1.72. This does not necessarily mean you have to do something, okay? You could just leave it at this. This is the value of the body mass index when the height is 1.72 meters and the weight is 72 kilograms. Okay? It's not necessarily a command for you to do something. You might have been taught that in the past. You could use this in other expressions and other functions. You can use notation like this to represent its value. Okay? Now, if we do want to know its value, what do? Plug it in. Okay? But it's not a requirement. It's not a requirement unless you really want the number. So is this right? And what do we get for that? What is it? 24-ish. Yeah, that sounds about right. I know, it makes me sleepy too.
24.3.
Thank you. 24.3. And I guess what would the unit be on it? So the unit would follow through the formula, right? It would be kilos per meter squared. Okay. Any other questions about the homework? So that's just a matter of converting the conversion from kilos to pounds and meters to inches. I think that's all that, yeah, W in pounds. So you'd have to look up what the, so how many pounds are in a kilo? Is that right? That was more. 2.2 pounds per kilo. And then how many inches in a meter? I'm not sure. So you'd have to look up those two conversions, and then that's going to give you some. Those two are going to together are going to give you some. That combining those, you should get this value 703. So if you combine those two conversions and you get 703, then you know you did it right. Is that who asked for that? Does that help?
Yeah.
That's all they're getting at there. Like so that you would put in inches and pounds instead of kilograms and meters. So you'd need an additional factor then to get you the same body mass index in kilos per meter squared. Yeah, so I think if you find this conversion and then you multiply these, oh no, you're gonna have to follow this relationship to get the 703. Does it work out? Did you remember doing it?
I remember doing it along with.
That's not Batman, by the way. That's my son. But Batman is the theme today, so I thought I'd show you a picture of my son. And there's trouble with Batman. Did you know there's trouble with Batman? Yeah. See, there it is. There's trouble with Batman.
Have you seen the Office in Ironwood, the one teacher writes before?
What's that? I thought that's pretty good, right? There's trouble with Batman. Okay. So.
My girl's in the country, so.
Okay. So let's review here. So we just got done with vector functions. We're moving on to multivariable functions. So let's just review. What's the general symbolic form and typical graph representation of each of these? What's the symbolic form and typical graph representation of a single variable vector valued function? What is that? A single variable vector valued function. Make sure we got our terms down here. So symbolically, how do we represent those? Remember how we represent? Vector. What's that? A single variable vector valued function? Anybody? Chandler, do you remember?
Is it just like back to back is equal to x or like a line?
So what is a vector valued function? What does that mean if it's a vector valued function? David, is that a hand? Yes, right. You have a exactly. You have a function that has one input that results in a vector. So if it results in a vector, how do we write it? Equals
t, comma, g of t, comma, h.
Okay, so f of t, g of t, h of t,
In chevrons.
right, as a vector, right? As a vector valued function, it gives vectors, right? It gives vectors, and then we call it. All right, and what kind of graphs do we get from these in general? What kind of graph do we get from that in general? Who remembers? What's that?
Curves.
Curves in space, right? These are curves in space. We put all these vectors in standard position, and then we let t change, and we get this laser light show, right? It's like the vectors point out this curve in space. Remember that? A week ago, we were working on doing those. Okay? A multivariable real-valued function. What's our, first of all, symbolic form of that?
It's that same thing, but it's more than just t. It's like t, comma, something else.
And do we get a vector out like this?
Oh, I don't know.
David, I saw first. What's that? Okay, so symbolically then, yeah, we get a real value. Symbolically, how do we show that real value? Yeah, right.
Z is equal to f of x, comma, y. In parentheses.
So here's our multivariable. Now we have two inputs, or we could have more, but we're focusing on two. And then what we get for that is not a vector anymore, but a real value, right? Real value comes out for any, and that's just like this quiz you just took, right? So the quiz dealt with this kind of thing. Two independent variables, and then you get another real value out for that. Or a set, you get a set of real values for combinations of the two input variables. Okay, good on the review? So we're talking about representations of these, and we talked about three kinds of representations of these multivariable real valued functions. Remember what the three we talked about were? Three ways to represent these.
Formula, function definition, and a graph.
Yes. So we talked about a formula. That was like what you wrote in for the quiz, the cost of renting a car. All right. A graph in R3. How do these? Oh, we didn't say how they graphed. What's the typical representation of a graph of these? What do you get? So what do we have? We essentially have an equation of x, y, and z. How do those graph in R3? Equations of x, y, and z.
Cylinder. No.
Could be a cylinder.
You use surface.
Surfaces, right? We get surfaces in R3 for these. We did not talk about this, or we're going to start with now. We're going to talk about that. What was the last one we talked about? That was like question 1 in your quiz, right? A table of values can represent a multivariable function. So values in the table are values of the dependent variable given combinations of the independent variables. Okay, so we've done 1, 2, and 4. You had a little bit of homework on those. So what about traces? Traces, we've seen this before. So traces for z equals k form level curves. And those level curves put together form a contour map. So we have done this, a little bit of this before. We're going to do some more. So let's look at this, okay? So here I have this equation, z squared equals x squared plus y squared. And I want to find traces that are level curves, meaning they're at the same, all at the same level. What will I do to do that? So what will I do to get traces that are at a constant level? If it's a constant level, then what am I setting constant here? If I want a constant like height or a constant level, which variable?
Any of the three variables equal to a constant.
You put z
So
in.
C.
But like think of a building, level. I want a constant level or a constant height. So it can't just be any of z, x, or y. Those would be traces, right? It's like holding any of the variables constant makes traces on the surface. That's true. But now I want a specific kind of trace that are level, meaning they're at a constant height. So that'd be z, right? So yes. Cutter, you said that.
I'm just confused. It's like,
I want other people to think about it too. So yes, you got it. All right. So what I'm going to do, I'm going to set. So if I set, so we can just do this on. We could write these down, but this is a kind of easy one for setting z equal to constant value. So for instance, if z equals 1, what do we get? Z equals 1 for this surface. I get
The circle
x squared plus y squared equals 1. Or I could write 1 squared if I wanted to. What is that? Circle, radius 1. All right, there we go. Kind of. Somewhere there. There it is. There we go. And then that would, so that circle then would live in the, which plane would it live in? In z equals 1, because that's how we got that circle, by setting z equal to 1. So it's the circle x squared plus y squared equals 1, and it lives in z equals 1. Okay, what about if z equals 3? What do you get? But what is that? Not what the number is. What is x squared plus y squared equals 9? What is that? Circle with a radius of 3.
That's 4.
I'm doing my best, Colin.
I thought you should know, just in case.
I know. I'm looking at it. Okay, here's 3. Okay, z equals 3. X squared plus y squared equals 9. And so where does that live? That lives in the plane z equals 3. That circle of radius 3. Okay, so if I chose all whole numbers of z, can I do negative z's in this? Can I do negative z's in this? Will it work? Will I get valid curves? Yep, I will. I'll also get more circles. And where will those circles live if it's negative z's? Yeah, well, yeah, Giorgio, below the xy plane, right? In those planes below the xy plane, you'll get more circles again. Okay, so what would the contour map or the level curves all graphed at the same time for whole values of z, how would you describe that? So if I graphed all of these at once, all these level curves over here at once. No, over here in R2. So what will I see if I graph all those circles for constant value or for whole values? Circles, and will they be equally spaced or unequally spaced circles? They'll be equally spaced because what? Because the radius increases as z increases, right? So z increases by whole numbers. Well, the radius is increasing by whole numbers too, because it's z squared equals x squared plus y squared. See that? What's that?
So it's increasing uniformly.
Yeah, linearly, right? So therefore for a constant change in z, you get evenly spaced circles. Okay, that's just for this surface though. So this is a way to represent. So I didn't really give you a function, did I? So this really, what function is this? Z equals function of x and y. To make it a function of x and y that's giving us z, what would it be? No, but what is the formula? Is it x squared plus y squared? Square root, right? And I'd have to take my pick. Either I'm doing the plus square root or the minus square root. Either I'm coming up with a function that lives in positive z or negative z territory. One or the other, okay? But not both, because then it's not a function, right? Function, you only get one result from any input, right? So what will this look like? So this is so what I'm showing you is this is a fourth type of representation of a multivariable function. This particular one. So here's the formula. We can make a table of values. What was the last one? Formula, table of values. Oh, the surface. And so this is still a fourth way to represent this function, because, like for instance, if I come here and say at the point 3 to 2, let's do 1, 2. Okay, here's the point 1, 2. X equals 1, y equals 2. How does that show me what the value of the function is? For when x is 1 and y is 2. So what's the value of the function here along that level curve? 0.5. Right? If you stay on that level curve, all these xy ordered pairs give a z value of 0.5. What about this? Z equals 1. Z equals 2, 3, 4. So if you stay on a level curve, you have a constant z. So at the point 1, 2, about what is the, you can see about what the z value is. Yeah, right, it's a little bit greater than 2. A little bit greater than 2. How do we know what it is exactly? How could we get it exactly? Use the formula, right? We'd use the formula. So f of 1, 2 is square root of 5, which is a little bit greater than 2. Okay, so that point right there, when x is 1, y is 2, we see from the level curves that it's a little bit greater than 2, because it's going from 2 to the 2.5 line. Okay, let's do another one here. Any questions on that? All right, so now I'm going to give you you figure out, oh, and by the way, so what's the surface? So now that we have the level curves, what surface will we get where the radius increases constantly with z? Is it parabolic cylinder, paraboloid? It's a cone. So it's just going to be the top half. If it were doing the z equals the square root of x squared plus y squared, it's just the top. And what's the bottom? How would we get the bottom? Yeah, so z equals square root of x squared plus y squared. The bottom is z equals negative square root of x squared plus y squared. It's two separate functions, right? You can't write a double cone as one function. It's got to be two separate functions. Okay, so I'm going to show you a contour plot, and you have to come up with the surface. Ready? Here we go. There it is. So that's the contour plot. This last line down here is 3. Somewhere in here is 2. On the actual x-axis is 1. And then up here is 0.4. So can you figure out what this surface looks like, and then maybe come up with a function formula for this based on your knowledge of functions? So what can you sketch the surface and write a function formula based on this representation of the multivariable function? This is a contour plot.
Okay. Because your space in between two is increasing exponentially.
You got a picture of it? So sketch. Anyone on their phone, you bring it up to the front. Talk, think, sketch. Talk, think, sketch. Talk, think, and sketch.
What's the 0.412? Starting at negative.
Those are values of z. So yeah, so these are that's the constant z. That's a level curve right there, and the z value is 0.4.
Okay.
And then this on the x-axis is a level curve, and its z value is 1. And then down here around negative 0.7, z value of +2. And then here, z value of 3. So I think these are, yeah, these are all 0.2. The lines are a differential of 0.2 in z. So 0.2, yeah, 0.6, 0.81, 1.2, 1.4, 1.6, 1.82, 2.2, 2.4, 2.6, 2.83. So the z values from line to line, it changes by 0.2. So remember, this is x, this is y, this is x, this is y. And these tell you the height z for those x, y ordered pairs on the lines. All right, who's got a picture? You got a picture yet? Let's see a sketch. Okay.
It's hard to visualize. The smaller the y value, the smaller the greater are further away. Further away. So it's obviously 0.2 z since you said they differentiate by 0.2.
Well, at z equals 3,
So
the y is at a negative y.
I think it's just 0.2 z is equal to y. Would it?
Can you draw it?
Yeah. So is y. So what is the angular on the top? Yeah. What is the shape of it? So sign thing originally, like that you're looking at with your coordinates.
Extra credit for the first 2 people who have a good drawing. You got it?
Oh, I need to show this Oh.
Go through the x-axis like that? You're going through the x-axis without zooming.
It could be like that, like a little skateboard.
Okay, flip it over, face down, face down. Colin got it. Extra credit for Colin.
No, dang.
Flip it over. You got it. But what do we get? Is that what we get in? Is that what the R3 representation is? A bunch of lines? So there's z values all in between there too. It's just these are certain z values, right?
Oh, so
So you have every z value in between here for 0.4 and 0.6, and every z value in between. It's just that you're showing where these particular z values are. Does that answer it?
I think so. Yeah.
Like
Because-
this.
That looks like a curve to me. Is it a curve?
It's a shape.
It's a shape.
It's a surface. That's what these lines are. It's like a.
It's really close. You just rotate it. You rotate it around. Nope.
Oh. Is it like this?
Right. Show me.
Oh,
Kind of, but it's.
It's like.
Yeah, you're kind of making it too hard, right? Like you're making it into a sign. There's nothing to do with sign. It's not sinusoidal. It's not sinusoidal.
basically just a factor of the shape of it, like a half rate type of thing.
Yeah. So there you go. That's good. That's good. All right. So what's happening here? So where is Z the highest? Where is Z the highest? Where is Z the highest value?
Negative.
Like as you're going in the negative y direction, it gets higher and higher and higher. So as we're going the negative, that's this way, right? What happens when you change an x? What happens when you change the x value? Stay at the same level, right? So what kind of surface will this be? So stay. It's the cylinder in the x direction, right? Where the y values are the highest here, and then when we get to the x-axis, what's the y value? 1, and then when we go into positive y territory, what's happening?
It's closer.
Getting closer and closer to 0. So high, so cylinder, high z values, then we get down to x equals the x-axis, we're at 1, z equals 1, and then we're going to get closer and closer to 0. So lots of you got it. This is an exponential cylinder. Which one is it? Does anyone know the formula that would give you that? It's exponential. That's a circle. So it's an exponential cylinder in z and y, right? Because it's a cylinder in the x direction, so it's going to be with z and y. Exponential function. Z equals. No, those are polynomials. Exponential means the exponent. The input is in the exponent. E to the negative y. So e to the positive y would be this way, right? It would get positive z as y gets positive, but we're getting positive z as y gets negative. So z is e to the minus y. So the point of this discussion is that those red lines are a complete representation of that surface and that function, right? It's a fourth way. We can represent with a contour plot in the xy plane. That's a full representation of this surface, i.e. z equals e to the minus y. Okay. Any questions on that? Who are my winners? Who did I tell you to flip over? Chandler? Who else? Colin was first. Chandler?
I don't know if you counted me.
Yes, you got it. So I think one other person got it. No? Oh, you were in the wrong direction. Yeah. So you had the right idea, but you were coming out. You made it cylinder. Yeah. So close. Okay. So let's talk about. So now we have an idea about these multivariable functions. Formula, surface, a table, or contour plot, right? So now we're going to start talking about calculus of those. Calculus. Rate of change of multivariable functions. So before we jump into multivariable functions, let's just do a crash course in rate of change. This may be a new idea to you, something that wasn't presented to you before. So we're going to review rate of change. Okay, so we're on a highway, okay? And the app on our phone tells you that you're currently moving at 90 feet per second. And that's a rate of change. It's a rate of change of distance with respect to time, right? Distance in feet with respect to time. Okay? So I want you to tell me, what is the meaning of that? The rate of change of distance with respect to time. What does it mean going 90 feet per second?
Every second.
He said every second you're traveling 90 feet. Agree with that? Is that your statement? Is that all you know from that? Is that the only thing you know?
At that point in time, you're traveling 90 feet per second away from your original destination.
Okay.
There's no acceleration.
There's no acceleration. So in a nutshell, it just tells you how far you go in 1 second. Is that what you're telling me? Tell you anything else?
Your speed's not changing with us.
Here's another way to say it. Every additional second means an additional 90 feet travel. Same thing? Okay, my claim to you is that's a very narrow meaning. That's very narrow. You know a lot more than that. Let me show you. You know a lot more than that. Do you know how far you go in 2 seconds? You see? You know. How far do you go in 2 seconds? How far do you go in a half a second? 45 feet. How far do you go in a third of a second? 30 feet. So you know a lot more than you go 90 feet in 1 second. How far do you go in a tenth of a second? 9 feet. How do you go in any variation in time, dx seconds? How far do you go in any variation of time? X? If dx is your little variation in time, in that variation in time you go? No. Look at the pattern, Kyle. In 2 seconds you go 180 feet. In a half a second, how are we getting these numbers? How are we getting the distances? What do you do to the number of seconds elapsed to get the number of feet? Multiply by 90. So therefore in dx seconds you go 90 dx feet. So you know so much more than how far you go in 1 second. You know how far you go in any variation of time, right? And by multiplying it by 90. So that's a good meaning for the rate of change. So here's the deal. This is what we're going to practice over and over again. For any change in time, the change in distance is what? 90 times that change in time. That's a good way to frame the meaning of the constant rate of change of 90 feet per second. For any change in time, to get the change in feet, you multiply it by the rate of change, 90. It seems so easy, but then when I ask you, I'll ask you over and over again, and you all look at me with blank stares. So take notes. Make your brain do as much work as possible right now to get this. This is the meaning of rate of change. And so that's a derivative. Whenever you take a derivative, you get a rate of change. And that value has this kind of meaning. Let the independent variable change a little bit. And the change of the dependent variable will be that rate, or that derivative, times the change in the independent. Okay, so what about with two variable real value functions? What's their form? They have form what? What's their symbolic form? Two variable real valued functions. How do we symbolize those?
Z equals x comma 1.
Right? Z equals f of x, y. And so when we talk about rate of change, it'll be the rate of change of what with respect to what, now given as z equals f of x and y. Rate of change of what with respect to what?
Z with respect to x times y.
Z must z with respect to x times y.
Times n.
What's that?
Times n.
Z with respect to x and y. Getting closer. Z with respect to, yeah. No, so we're just talking about just the quantities right now, not the not the differentials. So the z is right. So we look at the rate of change of z with respect to, yeah, basically x and y was right, but separately, right? X or y. Okay. So we're going to look at the rate of change of z with respect to x, and we're also going to look at the rate of change of z with respect to y. And in each of those separate cases, we're going to use that meaning that we just talked about. Given any change in your independent, the corresponding change in the dependent z will be the rate times the change in the independent. So here it is with respect to x. So given any change in x, we're going to get some change in z according to the rate of change with respect to x. So that follows from the last slide. And then what else could we write? What's that? That's right. So the rate of change is the m. The m is the rate of change. Given any change in y, multiply it by the rate, and you get the corresponding change in z. Raj, are you on your phone? Bring it up here and set it up here. Walk it up. The walk of shame. Of course. Thank you. Okay. So these are called, so what we have is, before you just had the derivative. Well, now there's more than one variable, independent variable, so these are partial derivatives. So that first one, mx is the partial derivative with respect to x. And my is the partial derivative with respect to y. So with a two-variable real value function, you have two derivatives. One with respect to x, one with respect to y. Each one has the meaning that we looked at the last slide about the distance time. Yeah, David?
So is it called partial because there's two functions?
There's one function, but two variables, right? So two independent variables. So we're like parsing it out, right? We're like parsing out just isolating the x, and then just isolating the y. And you get a rate of change for each. You get a derivative for each. Okay, so when we look at the partial derivative with respect to x, in order to, like I said, isolate it, you have to hold y constant, right? You're going to hold y constant, let x change, and then this will determine how z changes from that change in x. But you have to hold y constant. You don't want y to change also, or you won't be able to figure out where that dz is coming from, right? Same thing with this. When we look at a change in y, what do? Hold x constant. We're going to hold x constant, let y change. The rate of change will determine how z changes, strictly from a change in y. Okay, so notations for the partial derivatives. So these all mean the partial of z with respect to x. So this is like Greek lowercase delta. So instead of using d's, use this delta sign, and that means partial derivative. So partial of z with respect to x, partial of f with respect to x, or the easiest way is just, if the function is f, just write f subscript x. That means the partial derivative with respect to x. And so similarly for partial with respect to y, it's delta z, delta y, delta f, delta y, fy, all mean the same thing. Okay, so we're going to work on understanding and applying rates of change in the four different representations of these multivariable functions, right? So we'll start with, so here are the four different representations. So we're going to work on these rates of change, these derivatives in each of the four representations. So the first is function definition. So we'll come back to that one later. We're going to start with this one. This is a really cool multivariable function. It's the displacement in millimeters of a point on a guitar string. That's what this function gives when x is the number of millimeters from the end of the string, and y is the number of milliseconds after the string is plucked. And this is that function there, g of xy. So let's draw a picture to show that. So we've got, this is like the baseline equilibrium of the string when it's, at rest. And so then x is, say, distance down from the end. And then we're going to pluck it, and y is going to be the amount of time that's gone by. So if you froze time, maybe the string would look like this at one point. It's exaggerated, but it's going to, right? It's going to go back and forth really fast, vibrate. That's what makes the sound, right? The string's going to vibrate. And so maybe when you freeze time at a particular y value, so we'll call this x1 for this distance down the string, and then time is y1, then what would z be? So there's the point on the string x1 from the end. What would the z be? What quantity is the value? What do we mean by the displacement in millimeters?
How far away you are from the board of the guitar when you pull the string?
Yeah, so, well, not the board, but the at-rest position of the string. So this is like at rest when the string's not vibrating. So then this distance right here, that's z, which is what? G of x1, y1. Displacement, right? Because this is, it wouldn't necessarily be height, like if it was lying flat this way. So distance away from the original position. Okay, so here's the function formula for that. So what would it mean? So we want to find and interpret g of 70, 2.5, gx of 70, 2.5, and gy of 70, 2.5. So this little activity for you guys. This is an appropriate use of the calculator. Make sure your calculator is set to radians. These are all in the parentheses is radians that you're putting into those sines and cosines once you put those values in. Okay, so how would you find, let's do g of 72.5 first of all. How would you do that? How would you do g of 72.5? Yeah, okay, so that's easy. You guys can do that. So now let's do this partial derivative with respect to x. So what does it mean to find the rate of change function with respect to x distance down the string? What would that mean for algebraically finding that function? G of x. Okay, so yeah, we're going to find the derivative with respect to x, and then what does that mean for y? So what did we say? You're going to hold it constant. So you're going to follow all the rules you did before in Calc 1 for derivatives, but you're going to consider that to be constant, not a variable, for the partial with respect to x. So what will that derivative be? How will I take the derivative of that? Remember your derivative rules? Chain rule.
That was just a constant.
This is just a constant. So if you multiply by a constant, what happens in the derivative? You're multiplying.
It becomes 0. Oh,
You're multiplying. It's like the same as this right here. What happened to that 3 when you take the
it
derivative?
stays on.
Comes along for the ride, right? It just comes along as is. So we have 3 times sine of 765. That's all a constant. And so it just comes along for the ride. Now we've got the derivative of this. What's the derivative of sine of pi x over 100? Cosine of pi x over 100. Good. By the chain rule, then, times. Remember doing that? Remember doing the chain rule? Hopefully you learned that in Calc 1 and you practiced it in Calc 2. So the derivative, so this is all that stuff I put boxes around is constant, so it just comes along for the ride because it's multiplied, and then the rest of it, function of x, is just like the chain rule you've done before. Cosine of that argument times the derivative of the argument. Yeah.
X over 100 wouldn't that be a quotient?
No, because it's just a constant times x. Quotient rule is when you have a function of x divided by another function of x. If you had something x is in the top and x is in the bottom.
X squared over x cubed, for example.
Well, that will cancel. So like
Or
x cubed over e to the x.
with 3 sin x.
The 3 sine x, exactly. But this is much easier to see it as that constant times x, so no quotient rule. Everyone see how we got that derivative? All right, so now I want you to do, you guys practice, do the partial with respect to y.
It would be the same process.
Everyone practice, that's right. Same process, but now with respect to y. Everyone try it.
Do you want us just finding it or plugging in the numbers too?
No, we're just finding the function for now, and then we'll plug it in a second. So just do what we did for the partial with respect to x. Oh, I can turn some stuff back to you here. Okay, so work on it by yourself, and then if you need help, you want to check, then
Pi times pi x over 100 times 2.765 cosine 2.765 y.
all right, this is what's been offered up. If I can fit it. Fit? Why? Here's what Kyle has offered up. Agree? I got some nods. Good. Okay. So now let's. We're gonna split up some of you, so you don't have to find all 3. Everyone just find one of these. So if your birthday is January through April, find the value of the function. If your birthday is May through August, find the partial with respect to x. If you're September through December, find the partial with respect to y. Remember that inside the parentheses is radians. Make sure your calculator is set to radians. We're going to get these values, and then we're going to have fun. We're going to interpret them. That's the hard part. For the function value, I got 1.43. Anyone get that? My January through April birthdays. All right, for the partial with respect to x, negative 0.033. You got that? Sweet. And then for the partial with respect to y, 5.43. Good? Okay, so now here's the real test. What do these numbers mean? What do these numbers mean? So this one hopefully is pretty self-explanatory. Anyone want to explain this one? G of 70, comma 2.5 is 1.43 millimeters. Philip, you want to try that?
So, would that be 70 millimeters from the end of the string,
Right?
and at 2.5 milliseconds, the displacement is 1.43 millimeters.
Yeah, good. Right. So at that point on the string, at that moment in time, 2.5 milliseconds after it plucked, the displacement is so I think the string is like 100. No, I don't remember. Anyway, so let's call it 70 here. So at that moment, 2.5 milliseconds, that displacement right there is 1.43 millimeters. All right, that's the easy part. Yeah, David.
I just wanted to ask about
Sure.
G of X.
This one?
Was it 3 cosine pi x over 100 sine 2.765 times pi over 100?
It was 3 times the sine of 2.765 y times pi over 100 times cosine of pi x over 100. Is that what you asked?
I was asking.
So this is all constant, like we said, and then the derivative of sine is cosine, and by the chain rule, you leave the interior as it is, and then you multiply by the derivative of the interior, which is the pi over 100. That's the chain rule right there.
Why is it 3 sine times 3 sine 2.7?
Because all of this is held constant, because there's nothing to do with x in those. So that's all like a constant times our function. So constants times a function, when you take the derivative, just stay. They just come along for the ride. And then the remaining part that's a function of x, we apply the derivative rules. In this case, it would be cosine and chain rule. Does that answer it? Okay, so now, who thinks they could interpret this? Now remember what we said. What is let's practice 90 feet per second again. What does 90 feet per second mean? Can anyone do it? What does 90 feet per second mean? What's a good broad meaning of 90 feet per second?
The rate of change.
This is the rate of change of distance with respect to time. What does that mean? This is the rate of change of distance with respect to time. It's 90 feet per second. What does that mean?
Change of distance in 90 times the change time for a small rate of change.
That your distance changes by 90 feet for every second. Is that what you mean?
Okay, so given when a second goes by, you go 90 feet in distance. Is that a good meaning of that? Is that our broad meaning?
The change of y is equal to 90 feet times the change of x.
Okay, so yes, but that sounds like you're just reading the formula, right? So what does that formula mean then? So we'll do it one more time. See, I told you it'd be hard. Given any change in time, call it dx. What do we know? The resulting change in, not the change in dz, the resulting change in distance, position, sure, distance is, Giorgio?
90 times dx.
90 times as much as the change in time that you picked. That's the good broad meaning. Yes, you go 90 feet every second, but you know so much more than that. You know how far you go in any variation in time. You go 90, your distance variation is 90 times whatever variation time you pick. Okay, so now we got to apply that kind of broad meaning of this to this, okay? The partial derivative with respect to x at 72.5 is negative 0.033. So first of all, let's break down the unit. Millimeter per millimeter. What is this millimeter up here? Millimeters of what? From the end of the string? Nope. This is millimeters of displacement. Displacement. And what's this millimeters?
From the end of the string.
That's, yeah, per a change from the end of the string. Okay, so this is millimeters displacement per change in the distance from the end of the string. So what does this number mean? What does this number mean? Can we do it? Anyone want to try? Kyle.
I guess then for every millisecond, your displacement changes by 0.0326 or negative 0.0326 millimeters for every millimeter you travel away from the end of the string.
Okay. All right. So we had some good in there, a little bad, some good. The first thing was, what about when we're talking about this? What about the time? What about the time?
Constant.
We're going to hold it constant, right? So what time do we have? What time do we have? 2.5 milliseconds. So we can start by just saying at 2.5 milliseconds, right? So at 2.5 milliseconds. Yeah, sure.
So at 2.5 milliseconds, the displacement of your string will be negative 0.0326. You will have a string displacement of negative 0.0326 millimeters per millimeter you go from the end of the string.
Okay. So it sounds to me like you're still talking about 1 millimeter from the end of the string.
Or 70 millimeters from the end of the string.
Okay, so we're at 2.5 milliseconds. Yeah, we're getting closer. We're at 2.5 milliseconds, and we're 70 millimeters from the end of the string. And we're going to let something change. What are we going to let change? It's the partial with respect to x. It's the partial with respect to x, right? That's our independent variable. So we're going to have a little change in x from 70, dx. So, given I'm at 2.5 milliseconds and 70 millimeters down from the end of the string, I'm going to let x change a little bit. I'm going to do a little change in distance down the string. And what does this number tell me then? Max, want to try?
Okay. For time equals 2.5 milliseconds for every change in distance at the point.
Yeah.
Distance.
Good.
You have to multiply that by negative 0.33.
To get
To get the new displacement.
the new displacement? Almost. Is it the new displacement?
Change in displacement.
The change in displacement. So at 2.5 milliseconds and 70 millimeters, if you go a little bit further down the string, to get the change in displacement, you're going to do what? Multiply the rate times the change in x. So all together, here we go. At 2.5 milliseconds and 70 millimeters down the string, given any small change in distance down the string, the resulting change in displacement will be negative 0.33 times the little displacement that you picked, the little change in distance that you picked. In other words, at 2.5 milliseconds, dz equals negative 0.033 dx. And that's a little change from 70, right? That's a little bit of change from 70. You multiply by negative 0.033, that's how much change in displacement you'll get. What does it mean that it's negative? What does it mean that it's negative? The picture shows it, right? What does it mean that that rate of change is negative?
It's coming back to its original position.
Yeah, so the change in displacement, if it's negative, means the displacement is decreasing. Yeah, the displacement is decreasing at this point, just like I showed the picture. Okay, now you guys are going to practice at your tables on this one. Individual conversations. Everyone's either listening or talking. Got to get this, right? So what is the meaning of this? That GY70, 2.5 is 5.43 millimeters per millisecond. Go. Everyone's either talking or listening. Go.
At 70 millimeters down the stream. 2.5 times.
2.5 milliseconds.
It's the milliseconds. It's
So
the
70 millimeters on the string.
At 2.7 millimeters.
The change in displacement. The change in displacement. Per millisecond per specific point.
So it's DZ 5.4.
Okay, so. Okay, so.
You can set up this.
Or yeah, sorry, it's the long.
You're like us to have
That's the velocity. The string at that point on the plane. No, it's speed.
Yeah.
Speed. Or
Displacement is
Why-
how
why
far
bother
from
with
the
the
rest of
string?
the
Okay, so-
So dz would be a change in that displacement. It wouldn't be velocity. It would be a change in that displacement.
Well, it's 58 hours around the speed.
Yeah, well, I guess so. I guess if it's, you're right. I guess if it's millimeters per second, it's like the speed of that.
We don't need to.
So yeah, it's the speed of
Well,
it's the speed
I
of
actually like speed better. Yeah, the string, speed of that.
He works in the tandem center. I need help.
It's equal to speed.
It's not actually why mistakes. That's the problem. See, now you got it right.
Partial respect to y.
So much better figure out somehow.
Given a change of y. The resulting
DZ equals 5.4.
Sure.
So
Sounds good.
So Ken,
Your change in DZ
Huh?
when you change
so
dy.
you're at the 7.
No, your change in DZ is going to equals to
What about the 2.5?
times whatever you change in dy.
A little bit, right? We're going to increase time a little bit. What does the 5.4 tell us?
I'm gonna be honest with you.
But I start with very
It means we can let time change nothing that we want to.
Wait, 2 more.
What's that?
Yeah, because I have the class.
No, but 5.43 is the rate of change, right? What does the rate of change give us, right? If we let time change a little bit, that rate of change gives us something. Gives us change in displacement, right? The dz. What does that dz equal? How do we get that dz? Change in time, right? Exactly. So now we're going to put it all together. Right now.
It's slimmed enough. It's slimmed enough.
So y is your change in time, and then x is your change in distance.
Right.
Axis.
You know, come to think of it, I had it.
Is that
I should have just got to it for.
I literally said X.
But it doesn't depend on which one you change in respect to changes the overall changes in concept of units of the answer.
Yeah, that's confuse that.
If you interpret G with respect to X versus G with respect to this, you get a different units, you get different set of units every year. So it changes the overall perspective of the questions.
Yeah.
So they're gonna let you, give perspective.
So close, so close. Jake, did you get that? All right, Jake's gonna try. Here we go.
Okay. So quick question.
Sure.
Does it depend on whether you start with the displacement or the time, like when you're originally beginning?
In the
Because like
in
for
terms
the,
of
for the derivative of the x value,
Yeah.
you start at 2.5 milliseconds.
Right.
Your
we're
displacement-
starting at, for both of them, we start at there. It's just that we always, one of them we're just gonna hold constant, and the other one we're gonna let change a little bit. So in both cases, we're starting at these values.
Mhm.
For the partial with respect to x, what do we let change a little bit? Which one?
Oh, you hold y constant.
Hold y constant.
Yeah.
So you start with a little change in x, dx. And then you get what the resulting dz is. So here, we're going to start at those two values, and what are we going to let change a little bit?
Y, sorry.
Time, right?
Yeah.
So we're going to let time change a little bit, holding constant at the 70 mark. And what's going to happen? So tell us.
Okay. So add a displacement of 70 millimeters. Make it hard.
So x is not displacement.
From the end of
Yeah, that's the distance from the end of the string. Z is the displacement. The output
Oh,
of
no,
the
you're right,
function.
you're right. Okay. So at 70 millimeters from the end of the string,
Right.
Your displacement at 2.5 seconds is 5.43. Would you say millimeters per millimeter? And then
So does the derivative actually give us a displacement? Doesn't give us this gives us displacement. Partial derivative doesn't give us the actual displacement. What does it give us?
change
Change in
in displacement.
displacement. That's right. Variation in displacement.
Okay. For every change in time.
For any change in time. For any change in time. The resulting
The resulting displacement is
not displacement.
the variation of displacement
Right.
is 5.43
5.43
dy.
times the change in time that you picked.
Yeah.
Yeah, we're
Sorry,
getting there.
I
No, that's
thought
good.
I
You
thought I
almost got
repeated
it.
that whole thing. Sorry.
Yeah. Do you want to try again?
No, we're
Okay. Who else wants to try?
confuse someone.
Chandler, want to try? Okay. Chandler, here we go.
So at 70 millimeters from the end of the string,
Uh-huh.
the change in displacement
Change in displacement.
is equal to 5.43 your change in time.
5.43 times your change in time. At the time,
At 2.5.
at 2.5 milliseconds. At 2.5 milliseconds, yeah. Right. So the crux of it is this, that the change in displacement is 5.43 times dy, the change in time. So what's happening? As you go a little bit in x, the displacement is going which way? Down. And as you let time go by a little bit, the displacement is going at 70. It's a positive rate of change, right? So the displacement's increasing in time, decreasing in distance down the string. So if you let a little more time go by, what would you see? The string would be a little bit higher. Do you see that? And if you let a little distance, if you take a little distance down the string, your displacement's lower. That's because of negative rate and positive rate. One more person, interpret this number. Who wants to do it? Volunteer? Elena, you want to try? Oh, Giorgio, you want to try? Okay, it's okay to make mistakes. It's okay. We're all in this together. You trailed off at the end.
Yeah,
Oh, you're so close. That was really close.
is 5.43 millimeters per millisecond dy.
Times as much as the change in time. Yeah. Chandler, you're going to try? What? Well, you're going to do it. Or did you already do it?
I already did.
You already did it. Okay. Does someone else have their hand? Oh, Giorgio. You're going to do it? Yeah. Oh, come on, Giorgio. Bring it up. Yeah.
4 minutes.
There you go.
Okay, so 70 millimeters away from the end of the string,
Yep.
the change in displacement is 5.43 times the change in time at 2.5 seconds. Millimeters.
Awesome. Good. Okay. All right. So yeah, at 70 millimeters from the end of the string and 2.5 milliseconds, if you let time change a little bit, the resulting change in displacement will be 5.43 times the change in time that you picked. Okay, so let me show you the multivariable, or the surface that this is. So let me show you the surface. This is really cool. Good thing to end on here. So that function looks like this in R3. Where is it?
It's like my dog's back looks like my tail is. It's my, actually no, it's
Okay.
my cat. That's when we take back. Like,
So if I
think that function, just the shape that hits the uncanny valley.
if I pick a y value, so do you see that that plane picks a particular y value? What does that mean? So picking a particular y value in this function means what? What's that? Okay, setting y constant. And what was y again?
The time.
Time, right? The time. So I'm freezing time by focusing on that blue plane. I'm freezing time. And what does the gray surface give me? What are the z values of the gray surface?
Displacement.
Displacement of the string, right? So right now I'm at 2.42 milliseconds. So this is 2.42 milliseconds. Y. And so the gray gives me displacement of the string. And what was the x coordinate again?
No, it's the distance from the end of the
Millimeters down from the end of the string. So what does this show? When I take that blue plane and I cut it for a constant y value, a constant moment in time, what does the picture show now? Do you see what it shows?
It shows like at that time your distance from the end of the string and the displacement.
Yeah, David. Yeah. Every single displacement as what coordinate? Displacement is no, z is the displacement. The result of the function, the z value is the displacement. For x was? So what are you looking at right here?
This is the displacement.
When you look at for all these x values, you look at all these z values, what is that? I know, and when you put them all together, what are you looking at? What? Someone said it. So this intersection right there, what is that? That's the guitar string.
Oh, what?
That's the guitar string, right? At that moment in time. Because what? Z is the displacement up, X is distance down the string. So that gold intersection is the guitar string. So now watch. So now I can let time fluctuate. And what will you see?
You'll see it go.
So now that this is time going by, this is an exaggerated and way slowed down version of the guitar string vibrating. See that? Okay, if you need help with homework, you can email me or come an hour before class. I'll be here, okay?